So on the program, we have 20 minutes break, but we use it all up. So we're going to move on to the next one. Nachiappan is talking about typing in the while. It's joint work with instructors. I think he's here. Before you leave, you need to sign this. Yes.
Start?
Sure. Okay.
Alright, so welcome. I'm a PhD student at Chalmers, and it's obvious that I'm not John Hughes, so I'm the other guy. Yeah. So yeah, okay. So let's get started, right? So what's the problem here? Erlang is a great language, but it would be nice to have static types. Now, what do I mean by that? It was not designed with a static type system in mind, right? So what does a type system in Erlang look like, right? So that's kind of what we're going to look at. Why is this especially important for Erlang? Because no types in a distributed language mean distributed debugging, and nobody wants to do that. For example, you spawn a non-existent function on a remote node, and then you figure out it doesn't exist, and it crashes on that node, and then you have to go to that node to figure it out. Well, you might be like, hey, I can write error handling code, but that's the point, right? You want the compiler to tell you, hey, you've done something wrong, and no runtime overhead on your code, right? So we're not the only ones to be interested in this. This has been done by, a lot of people have looked into this, successful tools in this area. So there's been a lot of work and a lot of interest in this area. So one such successful tool is the Dialyzer, which you all know about, right? If you've seen annotations such as these in Erlang code, you can find them in the standard library. These are annotations that are used both as documentation and sort of help the Dialyzer info types. So let's take the Dialyzer for a spin. Consider this function, two functions here. One's a lookup function, it accepts two arguments, a key and a list of key value pairs, and then it returns, if it finds the first argument in the list of key value pairs, it returns the corresponding value, otherwise it returns none, right? It's a simple, straightforward lookup function, and find is basically an application of lookup, and it pattern matches with OK too. But note that lookup returns an OK and a float 2, and it's matched against a string 2, which means it's going to fail at runtime. It looks like a type-related error, doesn't it? Well, let's ask the Dialyzer. Oh no! What happened? Well, okay, so it failed, right? So it turns out, according to the Dialyzer, it's not a type error. Well, now we know why I'm here, right? So, okay, so the goal of our type system. Well, the goal of our type system is actually very simple. It's just going to stand there and say, ill-type programs shall not pass. That's it, right? So that's all that we're trying to do here. So, but when is something even ill-typed? What does ill-typed even mean? People say it like it's the most obvious thing, right? So, here's the definition. An expression is ill-typed if the type system cannot derive a type for it, right? The most interesting thing about this definition is that the notion of ill-typed depends on the type system, right? So, according to the Dialyzer, that was not a type error. That's fine. So, a consequence of this definition is also that a type system which identifies more type errors is going to reject more programs, right? So that's a cost we might have to sort of understand when we look at type systems. So the question is, what do Erlang programs written with the Hindley-Milner type system look like? Question of the paper, by the way. The question is not, can we accept or successfully type as many existing Erlang programs as possible, right? So this was the Dialyzer test, okay? Just putting a difference out there. So, but why Hindley-Milner? What is Hindley-Milner even, right? So it's a very successful type system. It's been applied to many functional languages, Haskell, ML, OCaml, you name it, right? It has a really strong type system, which means it identifies a large class of type errors. And it has really strong type inference properties. Now, this is particularly nice for Erlang because you don't have type annotations by default, right? Unless you add them. So it's nice to be able to infer all these types and free the programmer from having to add excessive annotations like Java or C++ or whatever, right? But it's not all straightforward. It has been noted before that applying the Hindley-Milner type system, there's certain difficulties with it. And this was noted by Simon Marlowe and Philip Wadler. They say, well, the difficulty with Hindley-Milner is that each type must involve a set of constructors distinct from other types. What are constructors? We don't have them in Erlang, right? So let's define them. So here's an algebraic data type. What is an algebraic in Haskell? What's an algebraic data type even, right? So it's basically a type system feature which allows you to define new types using user-defined constructors. This is a nullity constructor with 0 arguments, and this is a 3-argument constructor which accepts arguments of type A, tree A, and tree A. Where tree A is basically a type of a tree data structure where all the values in the tree are of the type A. A is just a type variable which says, I don't know, we'll see. So here's the corresponding Erlang ADT, right? It looks very similar, except that since you don't actually have constructors, you use atoms to mark them. And you give the arguments to the constructor, you pack them up as a record, as a tuple, right? And you just use the atom as the first field of the tuple to use it as the constructor. Okay, so how does this behave? So now that you've defined the ADT, you write a function which uses it, right? So you write the find node function. You say, well, the first argument is a node, the second argument is a tree data structure. You say, if you find a node in the tree, it's return true, otherwise return false. And as expected, the type inferencer says, well, without any type annotation, it says, oh, you gave me two arguments. It looks like one is A, one is a tree of A's, and the result is a bool. Straightforward, easy to see what's happening. But what's happening behind the scenes, right? So the idea is, let's try to understand what are the types assigned to these constructors. So consider these two data types. One is client and the other is server. The type of response is it accepts an integer because that's an argument, and it returns a term of type client, right? Because that's the data type we're constructing. And similarly for a request, right? It accepts an integer, it returns a data type of server. So this is how constructors are assigned type, but there's a problem here. This was what we saw earlier, which was observed by Wadler and Marl, right? So typically, in a contemporary implementation of Hindiman, like in Haskell or Camel, you cannot overload constructors. What do you mean by overloading constructors? Right? It basically says that the given constructor name can at most construct one data type, right? So, but in Erlang you cannot have this restriction because imagine saying OK must be unique, right? In all different contexts and various programs, it's impossible. You will have to either rewrite everything or it just won't happen, right? So the point here is that we need overloaded constructors if you want to apply a Hindley-Milner type system to Erlang. So we developed them. So consider these types, right? So the same type, server and client, but now you have an overloaded constructor exit, which, to complicate things further, also accepts arguments of the same type. So there's no way to tell what is the type of exit, right? What's the type of exit? Should it be PID R to client or should it be PID R to server? Yeah, we don't know. So we'll say, we'll let it have both. This is the main solution, right? We say it constructs PID R to T, where T is either a client or a server. So this thing is basically a type constraint. For you Haskell programmers, you might note it looks a lot like type class constraints, but it's just a type constraint saying that as of now we don't know what T is, but this is what it is going to be when we find out more. So I also want to point out here that this is not the assigned type, this is a derived type, right? So we'll see what that means. Okay, so this is called a deferred unification constraint. Okay, so let's try to derive the type of exit. So what do we know about exit? We know that it accepts two arguments and it returns a term of some type. Well, let's say those are some types A and B and T, right? So we know this is the structure of the type of exit. But we also know that this must be one of the two types which we saw earlier, which will be PID R to client R or PID R to server R. Right, so, but looking at the type constraint, in both branches, you can basically notice that A is always PID. If you just look at the first argument, it's basically saying A is either PID or PID. Well, it's basically saying A is always PID. So let's substitute A for PID. Now let's look at B. It says B is always R, so let's substitute B for R. Let's look at T. It does not agree, so there's nothing you can do about it, right? Okay, so now that you substituted all A's and B's, this part of the type constraint doesn't say anything useful anymore. So we throw it out. And we finally arrive with the type which we had assigned to exit earlier, right? So this is the type of exit. So all this which we sort of did by hand is basically an application of a proof procedure from classical propositional logic. More specifically, it's called Stallmark's proof procedure. And what we did here is apply something called the dilemma rule. It has a bunch of rules. One rule is called the dilemma rule. What it says is, if you want to prove a propositional formula which has n propositions, and if you don't know the truth of the proposition, what you can do is you can essentially branch over the value, meaning you can assign it to be true and false, and try to prove the formula for both cases. And eventually you'll end up with a proof tree of this form when you try to branch over different propositions. And what the dilemma rule in specific says, if so the leaves would be essentially truth assignments to propositions, right? So the dilemma rule says that you can take the intersection of all the values in the leaves and they would always hold. Well, intuitively all this is saying is that if you assume that a proposition is both true and false, and if you find out what holds in both cases, must hold regardless of what actually is the value of the proposition. So how does this matter? Oh, yeah, so the title of this slide should actually be Constraints as Propositions, but I think I'd rather do terrible puns than actual science. So anyway, so applying this to our scenario, what this basically means is that you get this proof tree of deferred unification constraints, and the leaves would either be solutions to these constraints, called a type substitution, or a contradiction which says there's no solution, which is a type error, right? So applying the dilemma rule here basically says the intersection of all these type substitutions must always hold. And this is what we did by hand. We said, oh, let's replace A by PID, B by R, whatever. So that was essentially a type substitution. Okay. So, but a Hindley-Milner type system can be quite restrictive. We need some ways of coming up with flexibility so that you can actually apply it to Erlang, right? Because there's quite a bit of flexibility in Erlang which you would like to retain. So let's try to expand this set of accepted programs. So this is one nice example of the flexibility. So typically in Haskell, for example, if you had a case expression, and if all your clause bodies, as we call it in Erlang, all of them must return a value of the same type. But typically you often find yourself doing something like return unit, just because you don't actually care what's being returned. You just want to do some crazy side effect, and you don't want to worry about the return value, right? So in this case we say, well, if you don't actually use the return value, then these types don't have to match. It's a small, nice convenience, right? Okay, so, but there are more difficulties. How do you assign a type to these functions? So let's look at the first function, right? Element. So it accepts an integer and a tuple can be a tuple of any size. Now in a Hindley-Milner type system, a tuple of different sizes have different types. A tuple of size 1 has a different type as from a tuple of size 2. So what should be the assigned type of element? We don't know, right? So it is the same problem with isTuple, spawn, and the list goes on. So in the paper we call these functions with dynamic type behavior. So once again, since we cannot deal with them, we get rid of them, of course. So for this we use a program transformation called partial evaluation. What it essentially does is it makes use of the static information available in your program and tries to eliminate this dynamic type behavior. For example, consider this expression, right? So this is a two-tuple constructed using f of x and g of x, and it basically returns the first component. So this can be transformed or partially evaluated into an expression where it has two components, t1 and t2, and you return t1, which is the first component. Semantically they're equivalent, but this does not have elements, so which makes it easier for the type checker. So we do this wherever possible, right? And it sort of is quite useful to do this. Okay, so what are the results? Well, let's look at this first. So it's fast. Okay, because why? Because Hindley-Milner type system is just straightforward unification. It's pretty fast. You don't have any subtyping here, right? So it does really well. It looks a lot like Haskell programs because kind of took this from Haskell. So, and the other thing is that, okay, so we've also applied it to a couple of libraries. So some of them OTP libraries and some of them, handwritten libraries. And it scales all right. In the sense that it does well and you don't have to modify code a lot, which is the most important thing. But notice that I said you don't have to modify it too much. In all these three cases, I had to add some lines of code, right? Like less than 3. So what were those lines? So going back to a previous example, so notice that these two are constructors of the same type. We know that, but I have to tell the type system that. So I add an ADT saying, maybe A, none, okay, A is of the same type, and then lookup has a valid type now. And now, once you have this ADT, you run the type checker, and then you get this very pretty type error saying, cannot unify string with float. Yeah. You get line numbers too. So, alright. but again, there are limitations to such a type system. You cannot do generic programs, right? Generic programming over constructors. What does that mean? You cannot use the wildcard pattern over the constructor, because constructor are tags for type inference, right? You have to specify the constructor. So this is actually a very common thing to do, provided the types of the arguments agree. So this is actually an implementation of the red black trees from GitHub, right? I think it's pretty popular as well. And so this program will just be outright rejected, saying I cannot unify these two types. This is a tuple, this is an atom. That doesn't make any sense. How can I unify that? So this program is rejected. Another limitation is, of course, that partial evaluation is nice, but it only helps when you have some static information. So for example, if you had, in your element example, if both your elements were dynamically computed, if you don't know the integer or the tuple, partial evaluation will do nothing, which means element is going to remain in the residual code, and your type checker, this type checker, is going to reject it. Okay, so that. Okay, so future work. So there's a lot more work to do, because we don't actually type modules as of now. We type only single module Erlang programs and exceptions. Well, exceptions should be straightforward. That's just what to do. And then, concurrency, which is also very interesting. It does not support concurrency, which does not mean it rejects programs with messaging in it. As we saw in the results, there was a distributed program which we were able to type check. That's because you assign types to these primitives, but you don't check that, like Joseph's one. So we don't actually check if messages expected are the same type as the ones sent, right? So, and also the other interesting work is gradual typing, right? Which would be interesting. So we have this really strongly typed set of programs. Now, can you expand this set by exploring gradual typing? That might be an interesting question to look at. Okay, so but there's more good stuff in the paper, I think. So we have really nice ways to type records, which I don't have time to discuss right now. We implement type classes for Erlang. They're pretty primitive. Programmers cannot define them, but there's no reason to not be able to expand it to allow programmers to define type classes. So this is how we achieve overloading for plus, etc., messaging primitives, etc., right? And there's a discussion on type errors. So it tells you what type errors actually look like, are they useful, how can you use them. And I'm done, but I still have more time, and I have more slides. Okay, so we saw constructors with type constraints, right? So look at this exit function, right? Is an overloaded function, but request on the other hand is a unique constructor of the server data type. So let's just take a look at X, right? So if you look at X, it has the overloaded constructor exit, so it possibly has this type, right, where you say X has the type T, but it can be either client or server, right? So, but the second pattern says request. Request we know constructs only something of the type server. So we add another constraint to it, saying that now T must be server. So this is an extension to the constraint, and now it's just straightforward constraint solving using the approach which we looked at. And you get excess of the type server, which makes sense, which is what you expected to show. And typing records. Turns out I do have that for records, right? So here's a record definition. So the tricky thing about typing records in Erlang is that they may not have type definitions, like in the case of ID, right? So these are basically just annotations either for documentation, maybe used by the Dialyzer. So you don't have to provide them. So if you want to use these definitions, you have to find a way to deal with them. So this record is essentially translated to an ADT, or an algebraic data type, as we saw earlier. So the data type essentially has exactly one constructor with the same name, and it has arguments which are of the same type as the fields, right, in the defined order. Now, what do you do when you don't have a type? You don't know, type variable A. We'll find out when we have more information, right? So in practice, what this means is that if you have an expression such as this, with name which matches the expected type, age which matches the expected type, and ID is a string, A gets instantiated with string, and the type of this expression is person string. Yeah, now I'm done. Thank you.
I'm wondering, so you had one example where you were doing something with a tree, and then you could just define a new ADT to solve that. You had a slide where you like, like way back.
This?
No, so you
right,
replaced something with this. So why can't you do this trick with empty and tuple?
Sorry, come again. This trick?
Yeah, so here you abstracted and you
you
defined
mean, why can't I do this trick here, right?
Yeah, why?
Right, so if you were to write these as two different cases where you say red and black, right? Then the compiler identifies that, okay, these are, it's going to be RVD in all three clauses, so it unifies them, everything's great. But what is a wildcard, right? You don't actually know. So if you were to assign a type to this, you also have to make sure that it's not a type error, right? Because it could actually be a type error. So it's not clear of how one should do that. If you do know how to do it, let me know. But it's not obvious. Yes?
So actually, in this case, empty is not over, right? It's only of this RVD type.
Oh, that's what he said. Okay.
Which means we know that
the
underscore can only be RVD.
That is
so that the type checker could replicate.
Yes, you could. Yes, you could. Oh yeah, you can do that. Yeah. Yes. Okay.
When you do use result of case expressions, or I suppose semantics is similar, is you have multiple function clauses.
Right.
You use return of that function. Then does it go down the enemy null route of enforcing that all clauses have the same type?
Yes. If you use it anyway, it's gonna.
I found this to be a difficult problem as well. Is you can do bounce checking on the size of tuples via guards related to expressions. Do you have some problems in sort of quantifying the size of tuples? Like you might say it's greater than 2. You say, but it's not 2, it's not 1, it's not 0 elements. Can you do any bounce checking?
Well, so we essentially treat them as completely different types, right? Okay. So there's no relationship between these types. Like you don't even have an ordering between these types where tuples of different sizes. Okay. So I think the problem does not exist there, but maybe we can talk about it. Yes.
The record stuff went by pretty quickly. I was curious. Is there a type function that's induced on that? So you have a polymorphic mapping from a record constructor to a concrete type, or is it the case that it unifies once, and the first time I see what an ID is, it's always that?
Well, the idea is that for this definition, you generate this ADD and you forget about that record. If that's the question.
Well, I'm interested in so A is just an ordinary unification variable.
Yes, it is. It's just a type.
There's nothing special with it.
So it is a parameterized type. So you could have a person bool, a person string, and so on.
Yeah,
it's not. This is what I was asking.
Yes.
Okay.
Does this also mean that you can, because you ditch the record, that you can do what you sometimes see in libraries of, say, accessing a common nth element? So you might say, like we call Erlang AST, say, like, did you find a record field as the first field in the record? And then to access the annotation, there's just a helper function that does element 2 of the tuple, even though it's a record. So that passes because you're sort of ditching the record and turning it into.
Yeah, that wouldn't work.
It would work.
Because this doesn't have.
Because it's just a tuple type, right?
Right, but the thing is, so it depends. So if you wanted element to work in that case, you would need the integer, absolutely, right? And then so if the partial evaluator works it out, then yes. Which means if it gets rid of element, then it works. If it doesn't, then it's not hard to just say, well, just treat this as a tuple. But as the current implementation of GitHub, it doesn't do.
So you want to say the type is this, and so we know that element 2 will select an integer.
Yeah, you might have like a pet type as well, where the second element is also a string.
Yes, but what's happening is that partial evaluation is taking place before type inference.
Oh yeah.
So it's not possible for information from the type inference to feed back into the partial evaluator. It would be nice to do that. Maybe next year.
Yeah, that's one of the things in future. So if you have a list of 2 elements, for example, the type checker knows that all the elements in the list, because of the enforced property, is going to be of 2 elements. But the partial evaluator has no idea. So it says, I can do nothing about it if you just access an element of the list. That's just one example.
any more.
Yes.
Just thinking about how Idris,
Right.
we have dependent types, and
Right.
you can, Erlang just yells that whenever you have like the value 42, and not just integer.
Right.
So how does that work? How does that behave if you have multiple function heads and you have like a literal, you have a 42?
Right. Do you mean can we add dependent types to this stuff? Well,
I
that would be
just-
cool.
just-
I would love to
just
do that.
Thinking if you thought about that.
But I think so. Type inference purely for dependent types is undecidable.
So you have a program that. I'm wondering if you set a type of as the literal 42.
Yes. Yes.
Okay.
I mean, if we
In the
start
same way
adding annotations, it would make sense to go towards that direction. But right now, there's no way to add annotations apart from ADTs.
Yeah.
You, in fact, you just cannot say this function has this type. Maybe even try to specialize. It's not possible. So maybe it's possible once you go towards more types in the program. But right now, I have to limit as much as possible to
Of course.
to apply it to existing program. Okay? I would like to do that.
Last question. Or last question. So normally type systems are linked to some sort of like semantic.
Right.
So what can you guarantee?
What can I guarantee with the types?
Yeah.
Like in type programs.
That at runtimes then your program will do whatever.
Right. So that's actually a good question. So as of now, right? So it's not formally specified, so you don't exactly know what kind of type errors you get. But you can make programs crash even though they go through this type error because of concurrency errors. For example, you say receive A to A, right? And you sort of treat that A as a string, but somebody just sends you an integer. Boom, it breaks. Right? So I think that's a problem of concurrency. But just within this sequentially typed subset,
Okay, so
I would say
it is sequential.
yes, in the sequentially typed, sequential programs, it appears that as type errors are defined by Hindley-Miller type systems, those programs will not crash. So it sort of inherits the whole Hindley-Miller philosophy, sort of extends it to Erlang and says what happens.
Yeah, I understand that.
Yes. So it's not formally defined for me to give you like one answer. So I think the best way is just sort of develop an intuition around it. Okay. Just like if they run Haskell and zero.
I have one more quick.
Yes.
What level do you do this analysis at? Do you do it on
Oh yeah. So this is implemented as a parse transform.
Okay.
So all the types are thrown away. You go back to proper Erlang. It accepts the AST, does some side effects, returns the AST as it is. Oh, the partially evaluated changes a bit, but who's complaining, right? So yeah, so that's what it is. There are no types which are propagated whatsoever.
Questions? If not, thank the speaker.